Hello, welcome to Chapter 1, Lesson 3. So this is the important equations for electromagnetic radiation. So we're going to have a look at three different groups of equations. We're going to have a look at the speed equation, the wave equation, and Maxwell's equations. So the speed equation. So this is where our inverse relationship between frequency and wavelength came from when we were looking at the electromagnetic spectrum. And this is just describing it mathematically. We know that all electromagnetic waves travel at the same speed, and we know that that is a speed of light. So we know that the velocity, the v, has to stay constant. So that leaves us with frequency f and wavelength lambda to deal with. So velocity has to stay the same. There's literally no option for that. So if our frequency increases, our wavelength has to decrease. There is no choice. So we have this inverse relationship. So you've got V equals F lambda. You might have heard of it as C equals F lambda, where you use C, which stands for the speed of light, which is technically correct as well. It depends which form you're used to looking at. So the wave equation, this is actually a collection of different ways of thinking about electromagnetic radiation and how we can manipulate it to get the information we want out. So the top one is where you've got your magnitude as a real number and your phase as an imaginary number. So these are the two parts that we want to measure, that we want the information of both of them. I'm an antenna engineer. I like magnitude plus the phase I. That's kind of my thing. So I have a real number, which is the magnitude, plus an imaginary number, which tells me the phase. I can combine these two into a Cartesian representation of amplitude and phase, and then I just have one number to work with. I like that. If you're more electronic engineering, you'll probably hear of I and Q, where I is the real part, Q is the imaginary part. It's the same thing, it's just a different way of looking at it, and to be honest, it depends what you're doing with it as to which one you pick that you want to use. So the bottom set of equations is looking more at the waveform, and this is where we split up that electromagnetic field into the electric and the magnetic field. So E is your electric field, it's equal to A sine omega t plus phi. B is your magnetic field, equal to A cos omega t plus phi. So the omega t plus phi bit basically tells you the rate of change of the angle. So this tells you how your electromagnetic field is moving. So if you want to know that omega is the angular frequency, the t is the time, and the phi is the phase. But that whole bracket tells you the rate of change of the angle, and the A is your amplitude. And this also tells us the relationship between the electric and the magnetic field, which is fine. There's nothing wrong with using these equations, and if I go back to my days as a physicist, these are the equations that I used to use. But you have to have two equations. You end up with two it's just too much of a faff. So you find that engineers pop them together and tend to use those top two representations. So Maxwell's equations. We literally cannot discuss electromagnetic radiation without talking about Maxwell. I think it's like actually written in the law. Maxwell's equations are an incredibly powerful set of equations that describe the behaviour of electromagnetic radiation. They form the basis of classical electromagnetics, optics, electric circuits, you name it. Anything to do with the wave, it's there. However, you're probably never going to have to solve them directly in your entire life. Not something that I don't think I've ever had to do. I make computers do that for me instead. But it's really handy to know what they mean and have an understanding that they exist. So Maxwell's equations is actually 4 different equations that Maxwell brought together, added some little bits in, and they've become known as Maxwell's equations. So the first two, you'll spot straight away that one's called Gauss's law, and one's called Gauss's law for magnetism. So the first one is looking at the electric flux, and it explains how that works within a volume of space. The Gauss's law for magnetism tells you about magnetic monopoles, that they cannot exist. So there's different forms of these equations, I should say, and I've actually shown you the differential forms because I think they're nicer to look at than the integral forms. but it depends what you're using. If you go on to do some of the future modules, when I'm discussing electromagnetic simulation solvers, then we will discuss both different types because you need both of them. But, you know, you need to know that they exist, not solve them, fortunately. The second two, you've got Faraday's law of induction, which tells you the voltage induced in a closed loop and how it's proportional to the rate of change of magnetic flux. And you need to finish the set off with Ampere's circuitous law, and that tells you about the magnetic field induced in a closed loop and that is proportional to the electric current plus the displacement current in the loop. So again, don't worry about learning these. Basically know that they exist, that there's 4 of them, and that Maxwell's equations actually underpin everything that you need to know. If you do want to go into them in more detail, however, there's many books out there, so go and have a look for yourself. The maths is really fun, so if you want a good challenge, go for it. So conclusions for lesson 3. We know that the electric and the magnetic field can be described mathematically in several different ways. We know that the magnitude and the phase can be described mathematically, again, in a few different ways. The way that you pick to represent it, it depends on what work you want to do with them. So the next video is actually going to sum up everything we've learned in lesson 3 before we're moving on to the second chapter. See you there soon.